Okay, thanks for inviting me and thanks for coming. I can only see 25 of you at a time, but seems like a great audience. So what I want to tell you about today is based on a paper that we just finished writing and submitting called Balancing Covariance in Randomized Experiments Using the Gram-Schmidt Walk. It's joint work with Chris Harshaw, who is a graduate student at Yale working with me and who's, I believe, on this Zoom meeting. Frederick Savji is a professor in political science at Yale. He's an expert in experimental design. Pang Zhang is a postdoc who's working with me. And I should mention that what we just put online is really the second version of this paper. The first version on arXiv reads more like a computer science-y paper. The second version is more geared towards experimentalists, is more geared towards statisticians, has more results, somewhat cleaner proofs. But if you are a computer scientist, it is quite possible you will find the first version more intelligible. But as I say, so it really, for me, the ideal paper would be a mix of the two because, as I said, we did manage to refine proofs in the second version, but that is written for statisticians. So here's my plan. I want to tell you, well, first, a little about randomized controlled trials and what you need to know about them. Tell you about the Gram-Schmidt walk algorithm and how we use it to improve randomized controlled trials. I should say the Gram-Schmidt walk algorithm, it was developed by Nikhil Bansal, Daniel Dadouche, Shashwat Garg, and Sachar Levitt. I see Sachar is here. I should say, when I saw the presentation of it at Stock in 2018, I really sort of fell in love with it. And I'm actually sort of embarrassed that it took me this long to find an application for it when it didn't actually occur to us to use it for this problem at first. And when it did, we then spent a long time trying to come up with a better algorithm before we realized eventually that this was in fact the right algorithm. Okay, so first, let's talk about randomized controlled trials. Let's say we're going to try an experiment to test out the effectiveness of, say, flipped classrooms. So our control group will be a professor teaching in the ordinary way, and the treatment that we're testing out is flipping the professor. We have a bunch of experimental subjects, which we are going to bring into the experiment. And let's imagine initially that they all look identical to us. In that case, what we'll do is we will assign some to the control group and some to the treatment group. And then observe the outcomes. Well, okay, first, it's a randomized controlled trial. We're going to assign them at random, and we will look at why we want to assign them at random in a moment. But we are going to make the assignment random. So, and in this case, imagine the teacher is trying to explain times 1 is equal to 1. So some of the people understand this after they have a little 1 in their head. The other people who are totally confused or they don't know what's going on, they may have a question mark there. And usually what you do at the end of a randomized controlled trial is you take a look and you see, did the group do the control group? So here were question marks among the control and more 1s among the treatment. We're likely to think the treatment flipped classroom is a better way to teach than 1 times equal to 1. Okay, let's put a model on this that we can then use for our analysis. I'm going to the Nyman-Rubin potential outcomes model. It is a very useful model and one that we can at least rigorously defend. So the idea here is that for each individual subject, there are 2 potential outcomes. One of them in the top of their head is what happens if they're put in the control group. The other one, say in the bottom here, is what happens if they're given the treatment. And under this model, we imagine that these potential outcomes are fixed. In that case, the only source of randomness in this experiment is the assignment to treatment or control. Now, some of you might imagine that it is sort of random how someone responds to treatment or control. And if you want to think that way, that's okay. just sample your random variable before we do any of this analysis. And then you will have fixed the two potential outcomes. So for all analysis we're going to do, we want to imagine literally the potential outcome next. The problem, of course, is that you don't get to see both of the potential outcomes. You only observe what you test. You only know this individual's potential outcome for the case that they're in the group. You only know this individual's potential outcome for the case that they're in treatment. And you can't see the other half of these entries. That's why we're using randomization. If I go back, if I could actually see in everyone's head, what are the potential outcomes? I would decide whether or not the intervention is good, but I would just sum up the number of one in the control case, and I would sum up the number of ones in the treatment case, and I would see which is larger. And that would be how I would decide which I like. But we don't get to do that. So instead we do a random assignment, and now we try to estimate which was better. So this is all fine and absolutely the right thing to do if all of the subjects look identical to you. But what if they don't? So in the statistics world, people call the differences between the subjects covariance. Imagine that you know something about each of the subjects and you can observe it before the experiment. So in this case, I'm imagining that some of them are old people and, you know, are newborns. You might presume that someone's age actually impacts on whether or not they understand that 1 times 1 is equal to 1. And in the way I drew of the newborns here, just have question marks in their heads. They have no idea what we're talking about. All the old people, yeah, they know that 1 times 1 is equal to 1. Okay, so what do we make of this? Well, first, let me point out the situation can be a little worse. Here are the potential outcomes. So the way these potential outcomes, they are just a function of variance. The old people all are going to understand in either group that 1 times 1 is equal to 1, and the newborns won't. Okay, so is this a bad experiment? Well, no, there's really nothing wrong with our procedure. Ideally, if we do a random assignment to treatment and control, you will get approximately the same number of old people in the treatment group and in the control group, and you'll see that there's really no effective treatment. But that might not happen. You know, it could be that you have too many old people in one group and suddenly you think the treatment is good when it's not. So the problem is the covariance can be correlated with the potential outcomes. If we suspect that might be the case, then we can get more precision or probably better estimators by actually doing the randomization in such a way that we balance the number of old people in both groups. You can see here I've just flipped 2 of the subjects where they're assigned. Now there's the same number of old people in both groups. So this is sort of a classic problem that's well understood in experimental design. If you think your covariates might be predictive of outcomes, you should try to balance them. And if you're just dealing with something binary, like gender, or I don't know, old versus young, you can do pretty well. Where things go awry is when you have high dimensional covariates, when your subjects can look very different in many different ways. Then classical techniques in experimental design don't necessarily help you out. Okay, so that is the intuition. Now let me try to be a little more formal. You again. The Nyman-Rubin model of experience. Yes, again, the assignment will be our only source of randomness. Whenever we make probabilistic statements in the end about the accuracy of our estimators, it will all under the randomness in the assignment. We'll imagine that we have 2 treatment groups for the rest of the talk. A can be test, B can be control. I might reverse them at some point. Get confused, it doesn't matter, they're symmetric. You know, testing whether or not a flipped classroom is good is the same thing as testing whether or not a regular classroom is good. Our 2 potential outcomes, we will label little a of I and little b of I. So little a of I is the outcome we would observe if subject I is assigned to group A. Little b of I is the subject we observe if subject I is assigned to group B. And all of our difficulties here stem from the problem that we can't observe both. Okay, when we talk about experimental designs, a design is the distribution of the partition into groups A and B. So equivalent, we could just define it as the distribution of A because B is the complement. So when people say design, that's what they really mean here. Okay, sometimes design refers to the larger context of the experiment and how you're doing your surveys and other things. But this part of experimental design, it just refers to the distribution of A. So for example, let me just mention some common designs. The most natural is uniform. Put each subject in group A with probability half independently. Well, that might be a little disconcerting. You could have different numbers of subjects in the two groups. So sometimes you take a look at a balanced design where A is actually a uniformly random set of half the subjects. One thing that's very commonly used in experimental design is matching. You try to match up pairs of the experimental subjects so they look similar. And then what you do, so literally you form a matching. It's a bunch of disjoint pairs I and J. And then you either assign, say, I to group A and J to group B, or I to group B and J to group A independently with probability of half. It's a very standard matching. All of these designs that it's described have the property that for each subject, the probability it's in A is 1/2. They just are not necessarily independent. And we're only going to consider designs that satisfy that today. So they're going to be 50-50. Each subject will have a half probability of being in group A. So one of the things people often want to measure from an experiment is the average treatment effect. So we will denote that by tau. It is literally the average of A of I minus B of I. I guess actually that's the effect of putting someone in control rather than treatment, but I flipped the two, sorry. Which would be the average of the A of I's minus B of I's. That's what we want to estimate. The problem is, of course, that we never get to observe both A of I and B of I. So we need an estimator. Here's the estimator we will use. It's the sum over elements I and A that get group A of the AIs minus the sum of the BIs. So that's really all of our data times 2 over n. And 2 over n is the right normalization constant. Let me walk you through it for those who aren't used to it. This is called a Horvitz-Thompson estimator. So in a Horvitz-Thompson estimator, you want to estimate a sum of things that you may or may not see. The way you do that, oh, sorry, wait, I see I have a question. It was, am I assuming that AI and BI are binary? No, definitely not. Our life is easier if AI and BI are binary, but let's not assume that. Okay, so we multiply an observation by 1 over the probability that we see it, or divide it by the probability that we see it. If we do that, then we get the sums right in expectation. Just to walk through it, if I want to estimate this tau, the sum of the AIs and minus the BIs, if I observe each of them with probability 1/2, that means we divide by 1/2 or multiply by 2 for each observation. That's how we get the 2 over n. This guarantees that our estimator is correct in expectation. The expectation of tau hat is in fact tau. I just want to take a moment to point out the estimator that I am not using. There's a very natural other estimator, which is the difference of means. I mean, you could imagine that what I would like to do is take the sum of the AIs and divide by the number of them, take the sum of the BIs and divide by the size of B and subtract them. That is a very natural estimator. It often is good. We're not going to analyze it for a few reasons. One, it doesn't necessarily get the right expectation. Heck, it can be infinite if B is 0. So it's also trickier to say things about the variance unless you have a very, very special design. Like if the group sizes are fixed, then you can say anything you want, but then it's the same as the other estimator. So we're not going to use that one. Okay, what we really care about, of course, is not the expectation. I mean, sorry, we want the expectation, but just getting the expectation right doesn't do much. We want to know how accurate it is. So how are we going to measure that? Is we want to know, say, what is the probability that tau hat differs from tau by too much? Oh, I see. Someone is saying that if the group of B is 0, then tau hat doesn't really exist. Well, let's just say that's an example of the sort of problem that you wind up with if, sort of variance can be very big if we're using that Hodgeck estimator. But yeah, then you can't measure a tau hat. And you probably wouldn't run that experiment. If you sample your groups and one of them is empty, you're going to decide you don't want to do the experiment, but you got to be a little more systematic than just doing that. Okay, so how do we get at the tail? So one way is you can measure the variance, and we're going to start by doing that. So if we want the variance of tau hat minus tau, I should remind you that since tau is the expectation of tau hat, that is just the variance of tau hat, which is the expectation of tau hat minus tau squared. So if we know the variance, then we can use Chebyshev's inequality to get a bound on the tails. We're often going to want better bounds, and for this we use sub-Gaussian random variables. So I'll remind you that tau hat is said to be sigma sub-Gaussian, the idea being it's going to act or be better than a normal variable of standard deviation sigma. Formally, well, okay, there are multiple definitions. The one we're using is on the exponential moment generating function. It's if for all lambda, the expectation of the exponential of lambda times tau hat minus tau is a most the exponential of sigma squared lambda squared over 2. This would be an equality if we had a normal random variable. If you have this, then you can use Markov's inequality, just like in the proof of the Chernoff bounds that most of us first learned, to prove it's unlikely the tail is too big. It's the most the exponential of minus lambda squared over 2 sigma squared. Now I should tell you that I've always thought of this as being a pretty good bound on the tail of a normal random variable. To the first order, it's right. On the other hand, I should mention there are some low order terms I could have drawn here, I would like to have here, that multiply this in the case of a normal random variable, but that you cannot get from this exponential moment generating function. So that is one reason I might one day want something better. I don't know how to do it yet. So the tails we can prove are not quite as good as the tails of a normal random variable, just close. Okay, so let's talk about the error. To make a formula for it, let's let z be 1. It's a vector that's 1 for the subjects in A, minus 1 for the subjects in B. Then we can write down the error as, well, I'll write n times the error down, as z transpose the inner product of z with A plus B, that is with the sum of the potential outcome vectors. We're going to use the sum of these potential outcome vectors a lot, so I'm going to call that vector mu. So the error is the inner product of z with mu. I'm going to walk through this calculation just briefly, if only because in 2 previous talks I gave on this, people got really annoyed that I was adding the potential outcome vectors together, but trust me, it's the right thing to do. If you write down n times tau, it's the sum of the ai's minus the bi's. N times tau hat is the 2 times the sum of the ai's for I and A, minus 2 times the sum of the bi's for I and B. And when you take their difference, you get the sum over I and A of the sum of AI plus BI minus the same sum for the I and B. So this is the right formula. I don't know why, but people instinctively want to subtract A from B rather than add the 2. Okay, so now that we know the formula for the error, we can compute the variance, and we'll get a nice expression for it. The variance is, of course, well, up to 1 over n squared, the expectation of the inner product of z with mu squared. Take that square, write it as mu transpose z times z transpose mu. Then this becomes a quadratic form, where on the outside we have mu, the sum of the potential outcomes, and on the inside we have this matrix I'll call capital Z, which is the expected outer product of this vector z with itself. And the key point here is we know this vector z, like we are choosing our experimental design, so we can control z. We don't know mu. So we're going to try to make z good, almost regardless of what mu we wind up using. So let's see how this variance plays out for 2 basic designs before we start introducing a new one. Let's first consider the IID case. So each z is plus or minus 1, probability 1/2 independently. We can compute the matrix Z. The ijth entry is the expectation of Z of I times Z of J. That is 1 if I is equal to J. So the diagonal terms are 1. The off-diagonal terms are 0 because Z of I and Z of J are independent, and they both have expectation 0. So Z, this matrix, really is the identity. That means that the variance of the estimator is 1 in n squared times the norm of mu squared. This is minimax optimal, meaning in general you cannot do better. For every design, any other design you choose, there will be some mu, some possible potential outcomes that could appear where there will be higher variance. The way you see this is note that the trace of Z is equal to n, because that's true for every design, because all the diagonals are 1. So for every design, all the diagonals are 1. That means for every design, the norm, or in this case, because Z is symmetric, the largest eigenvalue of Z has to be at least 1. So for every design you use, there is always a vector mu for which this ratio is more than 1. And that means there is always a vector mu for which the variance is more. Okay, so what does that mean? There is no generally better design than IID. The only way you can get better designs, or designs that perform better in real life, is if you are willing to make assumptions about the nature of mu. If you are willing to make assumptions about the potential outcomes, then you can do better, at least subject to those assumptions. So, and actually I should say one of my main goals in this work is to be sure that we are never much worse than the IID case. We want to be sometimes better when our assumptions in mu hold, but not much worse when those assumptions fail. Okay, so let's see a case where you can do better. And this is why people would use a balanced design. Again, think of assigning the same number of people to treatment as control. Your intuition is that's better. Let's make that formal. If you do that, Z is being chosen to be a random plus or minus 1 vector, the sum of whose entries is 0. That makes the matrix capital Z n over n minus 1 times the identity minus the all ones matrix, times 1 over n. Okay, this is one of my favorite matrices. Some of you know this is just a multiple of the Laplacian of the complete graph. We're not going to use any graph theory though. Let's see, once we know what the matrix is for a random balanced design, what we get about the variance of the estimator. So the leading term is going to be a 1 over n minus 1 squared. I'm going to say that is worse than what we had on the previous slide. Previously, we had a 1 over n squared. We've got 1 over n minus 1 squared. So the variance could be a little larger for some vectors than the IID case. But what happens in the middle here is we have the norm of mu minus its average entry. So if the mean of mu is 0, this is going to have worse variance than the IID case. But if mu is not centered, if the mean of mu is far from 0, then this will have lower variance than the IID case. And that often happens. For example, it could be that your outcomes are all positive numbers. If all of the A's and B's are positive numbers, mu will be positive. And it is quite possible that when you subtract the mean of mu off of mu, you decrease the normal line. So in cases like that, you would want a balanced design. Now, I should say, I think many of you listening to me right now are probably wondering, well, can't I just normalize the outcomes I see and subtract off the means? Probably. I'm wondering the same thing too. And again, there's error in estimating the means. And I should say, I'm new to this whole experimental design statistics business. So I'm wondering the same question. That is like one on my list of 1,000 questions that hopefully after I really master this material, I will understand, say at the end of the summer or something like that. Maybe that's just a warning. There's a lot I don't know in this area, but I'm learning. By the way, and Chris is on the line, so he knows more than I do. So my graduate student, Chris, has spent a lot of the last year learning statistics and experimental design. So if we get tricky questions that I can't answer, hopefully he can. Okay, so now let's see, how do we use covariance? So for now, we're going to imagine that each covariate for each subject is a vector in Rd. So we'll have n of them, one for each subject, x1 through xn. I'll assemble them into a big matrix, capital X. These covariates will be useful if they tell you something about mu. For example, like what if mu is close to the row span of X? Let's for now look at the ideal case. What if mu is actually in the row span of X? What if I can write mu as X transpose beta for some vector beta? In that case, the variance has a nice form. It is a quadratic form in the variable beta, and the matrix is X transpose, is XZX transpose. Now again, we don't know what this beta will be. We don't even know if our assumption holds, but if our assumption holds, we might not know beta. So we will try to make XZX transpose as small as possible. I guess I should first try to point out why this would be a win. That is, what I'm doing here, I should say, is I'm trading something about the norm of mu for the norm of beta. So let's at least observe that the norm of beta is probably less than the norm of mu, and at least it happens in some reasonable cases. So here's a reasonable case to think about. What if all of the xi's have norm 1? Okay, and the rows of X are orthogonal. Well, maybe that's unreasonable, but it's a model case. In that case, X times X transpose is equal to n over d times the identity. And then you can relate the norms of beta and mu. The norm of beta squared will be d over n times the norm of mu squared. So it'll at least be much smaller. Now, of course, this might not happen. The rows might not be orthogonal, but let them deviate a little bit. You'll still get that beta will have a much smaller norm, as long as d is much smaller than n. Okay, this is exactly what the Gramschmidt walk of Bonsaldo-Dushkarg and Lovett does for us. So I should write out the matrix XZX transpose in terms of little z again. It is the sum of the outer products of XZ times XZ transpose. The Gramschmidt walk algorithm, it takes as input vectors xi, and let's assume they all have two norm at most 1. And it samples a random vector z, signings, so that the expectation of the two norm of the expectation of the outer products is controlled. It is at most a number sigma squared that they derive in the paper to be 40. Okay, they don't exactly go for this variance term. They go straight for proving that xz is sigma sub-Gaussian. They prove it's xz is a sub-Gaussian vector, which just means that for every vector theta, if you take a look at theta, the inner product of theta with xz, that is a sub-Gaussian random variable. So that is what they proved in the paper, and they needed any constant for their application. They proved the constant of sigma being root 40. So I should just mention why they were doing this. Chachar can tell me if I'm wrong, because I never asked him. But if you read the paper, the reason they're doing this is not because they actually wanted to generate vector z that have this property. It's because they were coming up with an algorithm to make Banachik's theorem algorithmic. So Banachik's theorem is a fundamental result in discrepancy theory. It says if you have a convex body with Gaussian measure, say at least a half, and you give me any vectors x1 through xn that have norm at most 1, then there's a signing of them such that that signed sum is in some multiple of the convex body. It might not be in K, but it's at least in C times K for some constant theory. I think Banachik had C equal to 5. Banachik's theorem was an existence result. We don't actually, it didn't provide an algorithm in it. But Dushkarg, Lovett, and Nikolov proved that there is a way to make an algorithm if we can sample a random z such that the signed sum of z times the xi's is sub-Gaussian with some constant in front. That will then satisfy the guarantees of Banachik's theorem with some probability. And that is what Bonsaldo, Dushkarg, and Lovett were trying to do. So they wanted to sample so that they could get an algorithmic version of Banachik's theorem. Okay, we are trying to do this sampling so that we can, improve experimental designs. So for reasons that will become abundantly clear in a few minutes, we were not happy with the root 40. So after spending a lot of time trying to come up with a different algorithm, we eventually realized the right thing to do is improve the analysis of the Gramschmidt walk. And we proved that the constant sigma squared is actually 1. So that xe is a 1 sub-Gaussian vector. And that is optimal. You can't do better. And I might be able to tell you a little bit about how that analysis goes. It involves a different approach to analyzing martingales than we've seen used before. So to explain why that's useful, and why the Gramschmidt walk is useful in general, let's write out what the variance is in terms of the covariance. So in the ideal case, I said, let's assume that mu is actually in the row span of X. If it's not in the row span of X, let's take the beta that's closest. So let's let beta give the closest point in the row span to mu. Let's let epsilon be the error. So epsilon is a vector for me. It is the part of this of the potential outcomes not explained by the covariance. Mu is the sum. We can now write the variance term out. When you write it out, you get the matrix Z, but now with epsilon instead of mu, which is what you would have had if you were, well, not looking at the covariance. We have the matrix XZX transpose in a quadratic form in terms of beta plus a cross term. If we start analyzing this, we'll say that, well, the first term we'll say is at most the norm of Z times the squared norm of epsilon. The next term is at most the norm, again, operator norm of XZX transpose times the squared norm of beta plus some cross terms. It seems pretty clear that we want the 2 norm of Z and the 2 norm of XZX transpose both to be small. And the cross terms we'll worry about in a moment. I should mention these two goals are in conflict. You cannot make both of those arbitrarily small, but we'll try to make them both as small as we can. And the way we're going to do it is we're going to choose a trade-off parameter we call phi that tells us how much we care about Z and how much we care about the covariance. So phi sort of measures how conservative we are. When we set phi close to 1, we want to make sure we're never much worse than the IID design. And we set it close to 0, we really think our covariates are predictive. What we do with phi is we use it to modify the vectors we feed to the Gramschmidt walk algorithm. So instead of putting in xi, we multiply by multiple of an elementary unit vector and put that on top. These are what we call the augmented covariate vectors. I forgot to write that here. So we put in root phi times the elementary unit vector. So phi is 1. We're really ignoring the covariates and feeding the Gramschmidt walk elementary unit vectors, in which case it gives us a random plus or minus 1z uniform independent. If phi is equal to 0, we just feed it the standard covariance. So this is our input matrix. I should mention one other thing we do in the paper is we need to randomly permute the order of the vectors. This is actually not for anything to do with the variance or being sub-Gaussian. It turns out to be useful when we want to compute confidence intervals later. I think I will have time to tell you a little about how we compute confidence intervals. And this is one of the major gaps. And I will say where maybe one can improve on the Gramschmidt walk algorithm, or maybe, again, we should really just be improving on the analysis because it's a beautiful algorithm. And I don't have anything better yet. And believe me, we've tried. Okay, so what are the guarantees we get? For Z, that is the expected outer product of the assignment vectors, we get an upper bound in the Loevner order. So that means in particular that this matrix I'm drawing here, minus Z, is always positive semi-definite. So most the inverse of phi times I plus 1 minus phi times the Gram matrix of X. So this gives you some things immediately. I guess I should write out, like immediately from this you learn that Z is at most 1 over phi times the identity. And that tells you that the 2 norm of Z is at most 1 over phi. With just a little bit more work, you get that the 2 norm of XZX transpose at most 1 over 1 minus phi. So we can get a trade-off of these. As we vary phi between 0 and 1, we can trade off the 2 norms of these two matrices. Now you might wonder, I'm just dealing here with the matrices Z and XZX transpose. What about the cross terms? They turn out very nicely as well. if you actually translate through what we wrote here, it tells you that the variance of the estimator tau hat can be written as the minimum over beta of the 2 norm of mu minus x transpose beta. So that's as close as we can get to mu in the covariates times 1 over phi plus 1 over phi times the 2 norm of beta. So this just falls out from this formula. This is an upper bound on the variance, and we get sub-Gaussian tails. So now you might wonder, what should phi be? Well, first let me say, what I like to point out is if you set phi to be at least a half, this is at most 2, you're never more than 2 worse in variance than the IID case. Maybe you want phi, if you're very conservative, you might want phi to be more than a half so that you can say, again, you're very close to the uniform case. This is very important. If you're going to convince experimenters that they shouldn't use a uniform design, which is what they often use, you might want to tell them that, hey, this new fancy thing I'm suggesting can never be much worse. That was why we really wanted to get the sub-Gaussian constant down to 1. Because I didn't want to have a 40 here, because while for most computer science applications, 40 doesn't matter, here it would mean multiplying your number of experimental subjects by 40. And that's expensive or painful or impractical or impossible, depending on what it is you're trying to test. I think we'll never see phi like less than a 10th. There are applications in engineering where people have good reasons to believe that the covariates really are very strongly predictive, and then you might make phi pretty small. But the downside, if you have a model mismatch when phi is small, is huge. So probably we'll never see it smaller than a 10th. Okay, so that's how we use the Gramschmidt walk algorithm. Now what I want to do is, I get to tell you about how this algorithm works, which is fun. So what I'm going to do is I'm going to do it at a high level, and then I will drill down into explaining what these steps are doing. So the idea of this algorithm is it wants to make a vector z that's plus or minus 1. It's going to start with z being the all 0 vector, and then it's going to iterate, and at every iteration, it'll set at least one entry to 1 or minus 1. The entries are always going to stay in the hypercube, so they'll always be between minus 1 and 1. So the algorithm continues as long as there's some zi, an absolute value that's less than 1. And then it's going to update z by adding to it a vector u multiplied by a number delta, or at least let me tell you now that the expectation of delta is 0. So in expectation, z will always be 0, just some of the coordinates get set to 1 and minus 1. We're going to choose delta so that one coordinate has to go to plus or minus 1. The others are going to move. We're not setting one coordinate at a time. We're actually taking a step in some direction, but the others will stay within the hypercube. And ideally, although it's not exactly true, we would like x times the update to be orthogonal to x times the current z that we have. If you want to make such things possible, the xi's need to be independent. And so think about the dimension being more than n. In our case, where all of our covariates were running the algorithm, we appended some multiple of an elementary unit vector. They're all independent. So think of them as being independent. Let me explain in more detail how the algorithm works. We keep track of the elements that are not at 1 or minus 1. These are called the alive elements. Again, by the way, I'm following all the terminology from PDGL. There's always one element that they're going to call a pivot. You can think of it as that's the one we're trying to fix in each iteration. We set that to be the maximum alive element. We need some convention. Max or min is reasonable. There are a few others that could work. The elements that get to be plus or minus 1, we call frozen. Once they're plus or minus 1, they're going to stay plus or minus 1. They'll never change. We guarantee that by our update step. So we choose the vector u so that u of the pivot is equal to 1. U of I is equal to 0 for all the elements that are frozen. So that means the update step will never change a frozen element. And then there's an orthogonality condition that x times u is orthogonal to xi for all of the I that are not frozen other than the pivot. And this condition is going to help us achieve the orthogonality that we want. this turns out to be n equations and n variables, and it has exactly one solution, and it is solvable. So that is how the update direction is chosen. Then the update is we add delta times u to z. And I told you the expectation of delta is 0. And we want to choose delta so that one coordinate gets fixed to 1, the rest stay in 1 minus 1. And then at the end of the step, we update the set A. So the last thing for me to do is tell you how we choose delta. Well, I don't have to tell you. I already told you in some sense. The distribution on delta is determined by what I have told you so far. So there's only one way to choose this distribution on delta if you want to force one coordinate to 1 or minus 1 and have expectation 0. Let capital delta be the set of possible deltas that you could multiply u by so that the vector still lives in plus minus 1. Set delta plus to be the largest value in that set. If you set delta to delta plus, because it's the largest value, that means some new coordinate has to hit 1 or minus 1. Let delta minus be negative, be the smallest entry in there. Or actually, this is minus that, so it's a positive number. You set delta to be either delta plus or minus delta minus with probabilities chosen so you get expectation 0. That is the Gramschmidt walk algorithm. If I really want to analyze it, I should index things by t. And I realize, well, okay, why don't I tell you a little bit about the analysis? Actually, so I can decide how much. I should ask, when should I stop? Should I stop at 12?
I think you can go over.
Okay, maybe I'll go to 12:05 and then I can tell you a little more about the analysis. Okay, so first observe, let's assume the vectors are in general position initially. If you do that, you guarantee that exactly one variable is frozen in each step. That means there are exactly n steps. That'll make things nice. Otherwise, there could be fewer steps. You could have coincidental freezings. In that case, z of n is equal to the sum of the delta i's times the u of i's. Now, this is sort of a martingale. Ut is determined. The only random choices are the deltas. Ut is determined by delta 1 through delta t minus 1. And the expectation of delta t, given the previously chosen delta i's, is 0. So that means that the expected vector zn output by the algorithm is the 0 vector. Given that it's going to be in plus minus 1, and that the expectation is 0, that tells you in particular that each coordinate is 1 or minus 1 with probability a half. So that's how we know we get 1 and minus 1 with probability half, from the fact that the expectation of Zn is 0. One other useful fact I will mention that pops up in the analysis is one way of describing ut, the update at time t, times x, is it is the projection of the pivot vector at that point, x times p, the pivot at time t. It's projected orthogonal to the xi's for which I is alive at that time. In particular, because it's a projection, the norm of x times ut is less than the norm of xp, which is less than or equal to 1. That was by assumption. And I'm using the fact that projections only decrease norms of vectors. That will be important as I try to explain the analysis. Okay, so here are two crucial facts that make this whole sub-Gaussian thing possible. You can think of these as, this is what makes it possible if you're doing it on the real line. When p is the pivot, ut of p is equal to 1. So that fact, and the fact that at the end it's going to be plus 1 or minus 1, enables us to bound delta t plus and delta t minus. In particular, it tells us that when I take a look at delta t, and it's chosen from delta t plus and delta t minus, those two numbers are at most 2 apart. Because you can't push the pth coordinate plus 1 or minus 1. They might be closer together. That's when you fix something other than the pivot. If you combine that with the fact that the expectation of delta t has to be 0, that means the expectation of the square of delta t is at most 1. And that's sort of the first fact you need to even hope to get the variance right. To get the fact that it's 1 sub-Gaussian, well, Hufting's lemma considers exactly variables with conditions like this. Some of you remember Hufting's lemma is taught as part of the proof of Hufting's bound. So this tells you that delta t is 1 sub-Gaussian. That is the expectation of the exponential of delta t times lambda is at most the exponential of lambda squared over 2. Okay, let me give you at least a little bit of the intuition behind the variance calculation. So let's imagine a case where the ui's are actually fixed, so they're not changing, and all of the vectors x, u, t are orthogonal. In this case, you can show that for any vector theta, we want to measure the expectation of the square of the inner product of theta with xz and show it's at most the norm of theta squared. Well, assuming that the xuts are orthogonal, we can expand z into the sum of the delta t's times uts and write it this way. So we just get the sum of the expectations of the squares. Because I'm assuming ut is fixed, this is a fixed vector, I can move it there. And we can then get a term on the expectation of the delta t squareds, that's at most 1. So this is at most the sum of the squares of the inner product of theta with x ut. And that is now, because I'm assuming the x uts are orthogonal, and each of these vectors is norm at most 1, that's at most the norm of theta squared. That would be the intuition for the variance, again, if the ui's are fixed, but they are certainly not. They certainly depend on choices made by the algorithm. We can do something analogous for the sub-Gaussian bound. It's really almost just as simple. For the sub-Gaussian bound, what you need to prove is that the expected exponential of the inner product of theta with xz is at most this term here. So the way you do that is, again, you expand, here you don't even need orthogonality, the term z in terms of the sum of the delta t's uts. Okay, then we need to use the martingale property to pick off the last term and pick off the next one and pick off the next one and so on. And you can then say that this is at most the product over t of the exponential of the terms for individual time steps, where I should be putting like a condition on something here for the previous time steps, but let's ignore that. Here you can use the sub-Gaussian property of delta t. If ut is fixed, this plays the role of the parameter lambda. And what you get is this term is then at most the exponential of that squared inner product divided by 2. And now you just reassemble all the terms. You push the product inside to a sum, and you get at most the exponential of 1/2 the norm of theta squared. So this is at least some intuition for how things would go in a pretty ideal case. Let me mention you can be close to this ideal case. So what BDGL will describe as the ideal case is where at every step the pivot is frozen. So that means after P is chosen here, this is the element that is frozen in the update. If that happens, oh, by the way, I should mention that does happen sometimes, like if all the xi's are orthogonal. That implies that the x sub uts are orthogonal from this condition, because each x times u is orthogonal to the vectors xi that are still alive, and that's what the next iteration will be made of. In that case, the previous analyses basically work. I want to mention there's one feature of the sub-Gaussian exponential moment generating function, which is useful for this. Again, you have to work for the sub-Gaussian case by sort of martingale argument, peeling from the back forwards. And you use the fact that what we're trying to prove is this inequality. Divide the right and left-hand side by this. So you move that term into the exponential. Now you're trying to prove this is at most 1. You then write this term here as a product, and then you need to prove that each of these individual terms are at most 1. That is one of the really useful things to do with writing the exponential moment generating function this way. Because each of these terms you can sort of deal with individually. They just depend on what happens at time t. Okay, life is not always so easy. Oh, I see I have a red mark here because I had a typo on the slide. Let me just say there are phases in the algorithm that BDGL described. If the pivot is not frozen, at least it stays the pivot. Because the frozen elements are always removed from A and P, they set to be the max. of the elements in A. So they call a phase the elements you have within a pivot, and the steps with the same pivot. And you can argue inside a phase, and that's where all of the work is. And that's really the only point where we depart from them, I think, in the analysis. To argue the variance bound, you need to show that if you look at the steps in a phase, the sum of the delta squares, that is the step at P and the pivot, the sum of those squares is at most 1. And we can control exactly what it is within a phase. To get the sub-Gaussian bound is a little more subtle. Basically, we show that longer phases lead to better constants. And that's not quite formal. Let me say it this way. If you take a look at this term, which we need to show is at most 1 in each individual phase, here's something to think of. What if ut here was equal to 0? If ut is equal to 0, this term is equal to 0. And then certainly this is at most 1. Oh, I have a square I don't need. That's sort of what we do. We take the last ut basically and show it may as well be 0. And then the previous one and show it may as well be 0 and work back. Except the only trick is we can't really do it with the UTs. We have to argue in some orthonormal basis. It comes down to some crazy matrix inequality, which was sort of implicit in our first paper. But Akshay Ramachandran, who's a grad student at Waterloo, pointed out that what we were proving really is saying that some function is operator monotone decreasing on matrices. And it's not really so much a change in the proof, but the change in the organization that makes it much easier to read. Okay. I don't have time to tell you more about the analysis. Let's just ask, can we improve it? And see a few other things we can do. So first, you can't hope to improve this much on the variance. So again, we are proving now that the expected outer product of xz times xz transpose, the norm of that matrix is at most 1. Because it's a d-dimensional matrix, that would mean that the trace of this matrix is at most d. But this term here is just the norm of xz squared. So that implies that the expected norm of xz squared is at most d. You can't improve that bound. In general, there are matrices x where you can't do better. For example, if x is the identity. Any sign vector z you give me, this norm here squared will be d. I'll just mention, if you want examples that aren't squared, consider taking an odd number of copies of the identity, although I won't analyze it now. Okay, you can ask, well, okay, maybe there are matrices which you can't do better, but if I give you a matrix, on that instance, can you do better? Well, I mean, yes, empirically, yes. When we look at it, it sometimes does better, but I can't guarantee that. That's because Charikar, Newman, and Nikolov proved that it's NP-hard. So they proved that it's NP-hard to distinguish the cases where there is a vector z such that xz is actually even equal to 0 from the cases where for all z, the squared norm of xz is at least cd for some constant d. C. So once you know that's hard, you're not going to be able to make a guaranteed statement that you can ever do better. But when you do better, it would be nice to take advantage of it. And that's what confidence intervals are all about. So in the end, we don't just want estimators that are better than what you can get from some other design. We need to estimate how good the estimators are. That's what confidence intervals are about. Right now, what I'm going to do is I'm going to talk about how you estimate the variance. So again, we have estimate an upper bound on the variance. Recall that the variance we could write as this quadratic form in the vector mu times this matrix that henceforth I'll call Q. And the mu is the sum of the potential outcomes. So the upper bound we had on the variance is mu transpose Q mu. Let me expand that back into A and B. So we get a quadratic form in A, a quadratic form in B, and a cross term. We can estimate A transpose QA. It is a sum. If I write it as a sum over all I and j of the ij entry of Q times the AI times of AJ. We can estimate that using a Horvitz-Thompson estimator. We write it instead as the sum over the terms we observe divided by the probability I and j are both A. But there's a problem with the cross terms. I can't say much about Qij, Ai, Bi. That is, when I and j are the same, I have a problem. Because it is never the case that I is in A and I is in B. Because you'd never observe both potential outcomes. Okay, so the Horvitz-Thompson estimator fails for this unless we modify things, because you never observe both potential outcomes. Turns out the solution for this goes to a paper of Nyman from 1923. I guess 3 years from now, I'm gonna have to put the 19 in front of this reference. Nyman observed, okay, essentially let D be the diagonal of the matrix Q. And use Cauchy-Schwarz to observe, and that's, by the way, it's the problematic terms. The problematic terms are the diagonals when I is equal to j. 2 times A transpose dB is at most A transpose dA plus B transpose dB. You can use that, plug that in here. It really corresponds to shifting some diagonals in these terms. I add the diagonal to the matrix Q for the A term. I add it to the matrix Q for the B term, and I subtract it for the 2AQB term. This we can use a Horvitz-Thompson estimator for. In expectation, it estimates this, and that is an overestimate of the variance that we know. So this we can do, except for one slight potential problem. We still need all of these pairwise inclusion probabilities. For I not equal to j, what's the probability I is in A, j is in B, and the other possible terms? And we need them all to be greater than 0. And it turns out they don't have to be. This is the one thing I want to improve about the Gramschmidt walk. It is possible that some of these events never occur when you're doing the Gramschmidt walk. That is why we randomly permute the order of the vectors. We can guarantee that if we randomly permute the order of the vectors, then we at least have some bound bigger than 0. I'm not happy with this bound. It begins with a 1/4n, and that's bad. That affects the variance, times a constant depending now on our parameter phi. So we again need the augmented covariate vectors. And the proof basically is, we don't use much about the random pivots. We mainly use the fact that I has at least a 1/n chance of being the first pivot, where I is the one of I and j for which Q, the diagonal in Q is bigger. Then we prove, given that I is the first pivot, the probability for any of these events is at most 1/4 times this min of phi times this other term. And the analysis, well, it goes through the martingale argument, and I describe as some elementary linear algebra, maybe a little too much linear algebra, which is why we don't know how to improve this yet. But we really want something better. Why? Again, because for the Horvitz-Thompson estimator, this is our estimator of the variance of the estimator. This affects the average, this affects the variance of that, and we'd like that to be smaller. By the way, in practice, we did a whole lot of simulations. It's a large part of these papers. It is smaller, but we don't know how to prove it will generally happen yet. Okay, so here are ways I'd like to improve this work. First, we want better confidence intervals. So the bound that we are using, this upper bound on the variance, is often loose. And that is because this is an upper bound on the matrix Z, and it's often loose. On the other hand, once we know X, once we decide we're going to use this design, we can estimate Z. We can just sample enough, and we can figure out what this matrix is. If the variance is lower than this, when we then go to the sub-Gaussian bounds, which we need for good tail bounds, we would like those to be in terms of the matrix Z rather than the upper bound. Again, we can know Z. We know that better bounds are reasonable to obtain. Empirically, in our simulations, that's what they look like, but we don't know how to prove it yet. We also don't know how to check sub-Gaussian bounds by experiment other than through very, very painful, very extensive simulations. And it's even still not 100% convincing. So that's one thing we would like to improve. We don't know how to do yet. What's the improvement? It could be a factor of 4 on your expectation of the variance of the estimator. Does that matter? Yes. Again, we want to make estimators as accurate as possible with as few people as possible. It'd be nice to do that. Some other things we want to improve. Okay, I mentioned the tail bounds. Stronger notions of sub-Gaussian. Using the notion of sub-Gaussian that we're using here, you get tail bounds from the exponential moment generating function, but the right first order tail bounds, they're not the sharpest tail bounds, and the difference actually could matter if you really care about it. So trying to do this with stronger notions of sub-Gaussian would be great. Again, I have no idea how, because all of our proofs very strongly go through this. Another thing you might be able to improve is the trade-off between the norm of z and the norm of x transpose. So we know that the trade-off we get is within a constant of being optimal. Actually here, probably what you'd want to improve is not the bound we get, it's the lower bound. The lower bound we get right now really is the only fact it's using about z as the diagonals are 1. But it is a sum of outer products of plus minus 1 vectors. And then you can use the Goemon's lineal inequalities and treat this as a semi-definite programming problem. Maybe analyze it a la ARV and get better lower bounds. And I mean, so you might not be able to improve the Gramschmidt walk. You might just be able to improve the lower bounds to show they match. We don't know. Okay, so in practice, what do you want to do? Should you use our design? Well, what I would say is in practice, if you are able to collect all of the covariates to begin with, you can do extensive simulations on any design you want to try using for them and figure out which is going to work best. You can compute the variances empirically. After doing that, you can decide if you want to use this design. You might want to change your covariates. For example, you can include functions of the covariates. You don't have to use them raw. We don't have to only consider linear functions. You can add in small polynomial functions of covariates. Should you? I don't know. It depends on sort of your assumptions about the relations between mu and the covariates. You can weight the covariates. If you think some of them are more useful than others, you can put in weights in a fairly straightforward way. Just multiply them. Now, one question a lot of people wonder is, after we do the experiment, should we use some sort of regression or some machine learning black box to adjust our estimate of the treatment effect? It's a very natural thing to want to do. I will urge caution. Because if there's a lot of noise in your estimators, then you are fitting something to noise, and it's very easy to make your estimators worse by using any of these procedures. Sometimes you make them much better, sometimes you make them much worse. You might not know. By the way, I should warn you, you can find papers saying that this always improves things and you should always use these. Those papers are usually working in an asymptotic regime where n is very large compared to d, often exponential in d, often worse. I just say, as you read this literature, anytime you see the statement asymptotic normality, be very cautious. Often the asymptotic is a very asymptotic and not something you want to do. In our case, we might not need to. So again, if you take a look at our variance term, this is the result of a ridge regression. You are finding the beta that makes X transpose as close as possible to mu, and then adding, here's the ridge regression term, the norm of beta squared. Our upper bound on the variance comes from applying a regression on this treatment outcome vector in terms of the covariates. So in some sense, this regression is already happening, but it's happening in our design, and then we can use a naive estimator that you can then prove can never be too far wrong. So just the last few questions. What about balancing class sizes? Gramschmidt walk doesn't guarantee that. Often you want it. We have an algorithm in the paper, a variant, that does, but we have very few theoretical guarantees about it. So we implemented it, you can use it, it gets estimators that are a little better, but we don't know much about it. Probably you can prove something about it. But what about the online case? In a lot of experiments, subjects come in one at a time. You don't get to look at all your covariates up front. Can you do something reasonable in that case? Maybe you can. Maybe you can prove that in the worst case you can't. Maybe I'll just finish by mentioning there's an algorithm that a lot of people use they call re-randomization. This is, they pick at random. If they don't like the distribution they get, say the covariates, they do it again. They keep picking until the norm of x, z, is less than some threshold. As a computer scientist, I hate this because it's using an exponential brute force search to find something small, and that something is distributed corresponding to a chi-square distribution is almost never small. But I have to admit that if like the number of covariates is 400, you can do it on a GPU in a day, and you can find small things and you can sample. So that leads to the question of, is this algorithm bad otherwise? It depends on how small t is, but if t is in the regime that the Gramschmidt walk produces, I don't know. I was sure that I was going to prove it's bad, but I haven't been able to yet. So maybe it's actually okay. Maybe it's even better than the Gramschmidt walk design for small numbers of subjects. I don't know. Thanks.
Thank you very much. Oh, questions?
Yeah, can I ask a quick question because I have to
Yes.
run? The parameter phi, suppose you're a practical person, do you compute these with different fees and then make a choice? You said fee should be bigger than a half or around a half, but
at least, so yeah, if you don't expect
to someone who might be using this who's a medical person.
So, okay, so if, and I admit, I hope that every medical person has a biostatistician helping them choose this. And hopefully they look at their data and they take some fees and they simulate and they estimate the covariance matrices. By the way, we have code online for doing that. So you can take a look at what you're getting and see what you'd like. It really depends on how conservative you want to be. Unfortunately, I think this is going to take experience to make the decisions. Meaning over time, people will get an idea about in different contexts, just as they do now, which designs are best, which sort of fee are best, how predictive the covariates actually are. But other than that, again, I hope the medical person is talking to a good biostatistician to figure out how to choose this. And I don't have a great answer. If if you give us a model, we can tell you what's the right fee. So if you want to do something like assume your covariate, assume you have some linear function plus noise or something, you can actually derive exactly the right fee. But everything we write about right now is model free because we don't want to, deal with assuming a random model right now. That makes people very uncomfortable.
Okay, thanks, great.
I have a question. So where does it fit in the whole business of designing experiments? I guess you started, as you told us last week, from a particular application of some medical issue, but it's a vast world, this design of experiments, and is it part of a direction about changing the approach to modeling design of experiments? Is it a particular case, or is it
So my guess, so my guess is you want to use this idea or something like it almost anywhere where you are doing a randomized controlled trial and you can't observe both outcomes. So that's medical experiments, a lot of the experiments they do in economics, a lot of the experiments they do in political science. Like that's why my co-author, Frederick, is a political scientist. He does experiments on vote, in political science. There are a lot of famous experiments in voting behavior and things like that, where you try to nudge how people are going to behave. So there are a lot of places where people do experiments, and you may want to do this. Does it change modeling? That I don't know yet. And really, we're just at the beginning of this. But certainly where you have covariates, where you know things about your subjects, A/B testing, if you're changing how Facebook decides to present a page to you, might be reasonable. Although, yeah, there are all sorts of places where you're doing experiments, and this is a reasonable thing to try.
Right.
Any more questions?
Okay, well, thank you all for coming.
Thank you so much for the lecture.